My name is Dr. Srinivasa Murthy, and I'm going to take up the course on computer system architecture. Today on a module, register transfer and micro operations. Particular topic on the contents related to register transfer and micro operations. Register transfer today we will discuss one by one. So what is register transfer language? A register transfer language, a digital system, is an interconnection of digital hardware modules that accomplish a specific information processing a task. So here what it has been defining, a digital system is an interconnection of digital hardware modules that accomplish a specific information processing task. So here what are the interconnections we are going to have in the hardware modules? One, we know we are going to have an input device, and this input device is going to connect it to CPU, and we know that the CPU generates an output to the output device. Is it not? So here it is. Here what is defining a digital? No, this total is an digital system which is interconnected of digital hardware modules. Input is one hardware module, output is an hardware module, CPU is one hardware module, and the CPU is also connected to the memory device. It is also connected to the memory. Getting it clear? So every part which is connected to CPU is an hardware module. Why we are connecting? To complete and accomplish a specific information task. That's what the first point in the register transfer language. It has been defining that it is interconnected. It is interconnected of the digital hardware modules. Input is one hardware module, output is an hardware module, and memory is one hardware module. Central processing unit, CPU, is one hardware module. So interconnecting all these devices to accomplish a information processing task is known as digital system. Getting it clear? Next, digital system uses a modular approach. Now this is a digital system. Here what it is defining here, a digital system is a modular approach. How this modular approach is performing? The modules are constructed from such a digital components as registers, decoders, arithmetic element, and control logic. Now, digital system uses a modular approach. It is defined. What is this modular approach? Again, it is constructed of a digital components. What is defining here? Like registers is one digital component, decoders is one digital component, arithmetic elements is another component. It has been defining, and control logic is another. So next, what is defining? The operations performed on the data in the register. The operations are performed on the data in the registers. So here, registers is one. What we have to understand here is registers are data storage will be done. Now, how it will be done, we will see an outline here. Now, here the registers is a device, means the registers as a part of digital component. So, CPU, central processing unit. In the central processing unit, if you consider, the first thing is it is going to have is decoders. Second one is arithmetic logic unit. It is defined here as arithmetic elements. Third one is it contains a control unit. Here defined as control logic, and main on which the data operation is performing are registers. We're getting it clear. So when we want to perform some operation on the data which is stored in the registers. Before that, we have to understand what is the importance of the decoders, what is the importance of arithmetic logic unit, what is the importance of control unit. Then automatically understanding one point to another point in simple manner, we can understand the once the data storage in the registers, how it will be processed, it can be understood. So next we will see, as per the definitions, we'll discuss first the registers point here. So what are registers here? Registers is not a new concept. In the digital logic design, we studied the sequential circuits and combinational circuits. In the combinational circuits, we discussed about shift register. What the shift register basically defines, it takes input data and it generates output data. The data can be present in the shift register, either it may be 0 or 1. The data presence in the shift register, what is the concept? Till the supply, the power is present, the data can be resided in the shift register. If there is no supply, the data, whatever is stored, either the value may be 0 or 1, it will be lost. So, a group of bits is called shift register. Group of bits means it's a 1-bit register. Now, there is 2 bits. It's a 2-bit register. If you are having 4 bits, then 4, we say it's a 4-bit shift register. Now, what this each block it contains 0 or 1. In fact, this we call it as flip-flop bits. We call these bits called flip-flop bits. Flip means 1, flop means 0. Flip means 1, flop means 0. So each flip-flop contains a maximum storage of either the value of 0 or 1 in each bit position. So if it is a 1-bit storage we having, we call it as flip-flop storage of 1 bit, we call it a 1-bit shift register. If flip-flops are 2, then we say it's a 2-bit flip-flops. The values in the flip-flop may be 0 or 1. If we have 4, it's a 4-bit shift register. Always the data in the shift register is taken from the left and data output will be taken from the right of the shift register. So in this shift register, if you discard the name shift, what's the name left out? Register. In this way, we define the storage of the registers as name taken out from the shift register, and we started using it as a register in the digital systems. I hope this should be clear for you. Next, what is just now we've seen how the name register being defined for data storage in a digital system. Next, here we have to understand what is the size of the register. What is the size of the register? The size of the register depends upon the size of the data bus, of that particular digital system, If say the size of the data bus of a digital system is 4-bit, then the size of the register is also equal to 4-bit. If size of the digital system of the data bus is 8-bit, then size of the register for that particular digital system will be 8-bit. It depends or varies with respect to the size of the data bus which we are performing operation in a digital system. It varies from digital system to digital system. Today we are calling it as an computer systems. So in this way, the sizes are defined in a digital system. The most popular successful data storage in a digital system, register storage is 8-bit. That means the size of the data bus operation on which the successfully performed more frequently is of 8-bit. 8-bit, how we define an 8-bit? Means 8-bit in a digital design we call it as 1 byte is equal to 8 bits. As all of us studied and discussed this particular concept in the digital logic design, we know nibble is equal to 4-bit. Okay, byte is we define it as 8-bit. If it is a word, it is 16-bit. If it is a double word, then we define it as 32-bit. If you see, it goes on increasing in a pattern from nibble to byte, byte to word, word to double word. So in this way, the data bus of a digital system, what way we define, in that way, the size of the registers also will be defined for the digital system. So for present example, we are considering it as only 8-bit. We are defined only with 8-bit of data. So this 8-bit means the register size is practically here. 8-bit means here now it's nothing but it's shift register. Now we can define it is 1, 2, 3, 4, 5, 6, 7, 8. Now in this way, the flip-flops, each one is a flip-flop. It starts. So it is flip-flop 0 to flip-flop 0 to flip-flop 8. So maximum 8-bit data you can store. Now, what is a flip-flop again? You may have it out. It's a basic electronics. One flip-flop is equal to one transistor. Is equal to one transistor. Transistor, the basic principle of transistor is still supply is there. In one transistor, one digital bit of value signal can be stored. The value of that signal may be 0 or 1. So one flip-flop is equal to one transistor. So backend how hardware is we are defining for registers. If we are using 8 flip-flops, then the register are equivalent to the number of flip-flops. So 8 flip-flops, 8 transistors are practically present in which 8-bit data can be stored. The value of data what we are storing, it may be 0 or 1. In this way, the data storage in the registers are done in simplest way. Hope in a better way it has been clarified. Next, once we define the size of the register is 1 byte. In the third point, you say the operations are performed on the data registers. Now, if I am having only one register, then only we can store 8-bit of data. Now, if we are having more number of registers in a digital system, then more data can be stored. So, there may be in any digital system either 8 to 12 registers are taken. Now, you may question here, why we have to take 8 or why we have to take 12. So there is no hard and soft rule. There can be n registers. If you define more registers internal to the digital system, then the data accessing from these registers, it takes more time. Then the computing will be delayed and generation of output also default link will be delayed. So we'll define so many registers internal to the digital system which are sufficient in the given speed it can access and perform operations. Rest of data, it will be there stored in the main memory. So either it will be 8 registers or 12 registers to maximum extent where it should not affect to the speed of the processing of a digital system is not going to be affected. To that level only the registers are taken into account. That is another point. It should be clear here. Next, here. Now, what is defined? The functions built into the registers are examples of micro operations. Functions and now there is a micro operations. Shift, load, clear, increment. These are the different types of operations in a digital system. A micro operations will be performed. Until now, what you have to get clarity is here the functions built into the registers are example functions. And now I said the first part is more should be clear to you. The registers are more. It can take out name from the shift register for data storage. Now the same data storage shift register, if you take example, if instead of 8-bit, I'm taking it here 4 bits for better understanding. Now here in this 4-bit, 4 shift flip-flops are used. Now what I'm doing is, first there is a data present is 1 0 1 0. Now what is the possibilities here? This is left, this is right. Now to the facing of the screen, my left hand will be always to the left and right will be right. If I want shift right means the values now, these values have to rotate shift by once. So here what happens when I shift default shift right means the values here I have to shift. So what happens initially, the value in the least significant on the left side, the bit size is here 1. But when you move to the right, this value becomes 0, this value becomes 1, this value becomes 0, this flip-flop value becomes 1. What is the condition? This bit will be lost because it is moving out. There is no other flip-flop to store this particular data. Naturally, this bit will be lost. And once you shift right, the new value in the data is going to be lost here. So in this way, the shift register operations are performed. Same shift left, shift right are performed. Next, load. Load means the registers loading the data. You want to store data. Then what happens? This load operation will be used to store. Next is you want to clear the data in the registers. Clear data, or simply next one is we come after shift operation. Next we go to load. What is the load operation? This load operation indicates read data from memory into the register. Read data from into the memory to registers means now these registers are part of CPU, digital system central processing unit. Now there are limited registers. The main data storage is in the memory. The main data storage is in the memory. Whenever the next and the present data operation is completed in the digital system and new data, the operation has to be performed. That particular data you have to read from the memory to registers. The data, whatever you are reading from memory to registers, we use the operation called load. Then the data from particular memory location will be loaded into the registers to perform next operation in the arithmetic and logic unit of the digital system. Clear means if you are using a clear operation, whatever the data you store in the register, if it is 0 1 0 1, if you say clear, in the register this particular value is stored. If indicate a clear operation, then what happens by performing this, the value in the register, once you use a clear operation, it becomes all values becomes 0 here. So in this way, next is increment. If the same value is saying you are incrementing, next value what happens when now this is 0 1 0 1 is equivalent in a digital system, the binary pattern, it is equivalent to 5. If you say increment, it goes to incremented to 6. How it increments? To this 0 1 0 1, you are going to add 1. 1 1 is 0 with 1. Now 0 1 1, which is equal to 6. In this way, these are the different types of operations. There are more operations. Is a case study we defined in this particular register that the register in this particular discussion, you should be very much clear that in the register transfer language, first we should understand what is a register. A register is defined from a combinational circuit of the digital logic design called shift register. This shift register is designed with a group of flip-flops. If it is a 1-bit flip-flop, we say 1-bit shift register. In that only single bit value can be stored. Either the value may be 0 or 1. If a 2-bit shift register, the value in the shift register may be 2 values can be stored, either 0 or 1. If it is a 4-bit, 4 flip-flops will be there. Now each flip-flop, what is a flip-flop? Is an external. The flip means 1, flop means 0. How the backend, the storage of flip and flop, it's basic electronics. We use transistors, which can store each transistor can a single bit value, either 0 or 1. Now, if it is a 4-bit, 4 transistors. These transistors backend in electronics, it supports in the front end. These 4 transistors, we are discussing it as a flip-flops, where the values in a binary form, zeros and ones, in machine language, we are going to store in the registers. So in this way, the register name is defined where data can be stored. Next, we discuss that the size of the register depends upon the size of the data bus. If size of the data bus is 4-bit, then the register storage maximum of 4-bit value. In the maximum standard operations, 8-bit is taken out. So 8-bit register means 8 flip-flops will be there. A 8-bit data storage in a register, we also call it as 1 byte equivalent to 1 byte. A 4-bit means nibble. So on goes on. So in this way, the basic operations, what we can do in a register, micro operations at the back end, we call it as shift operation. We see in an example, load, clear and increment. So this is one of the basic register transfer operations have been discussed with respect to introduction of the register transfer language. When you go to the next slide, it gives the previous slide, whatever we discussed, it creates a clear picture. You can see the micro operations is an elementary operation performed during 1 clock pulse on the information stored in 1 or more registers. Now you can see R. Now R is defining R is a function of R2. R is a function of R2. What is the function here? A function can be shift, a function can be load, a function can be clear, a function can be increment, it can be add, it can be increment, it can be complement, and it can be a logical operation as OR, XOR. There are n number of operations which we define for this particular ALU. This register supports the particular function operations which will be executed in the ALU. The abbreviation of ALU is arithmetic logic unit. This operations has to be completed in 1 clock cycle. It has to be completed in 1 clock cycle. So, what is a micro operation? You will have a problem to understand what is a micro operation. This micro means what? 10 to the power minus 3 backend. So, in that particular speed, that particular operation has to be completed. That means here the timing cycles we define is in the microseconds. We define in the microseconds. As a human beings, we are habituated to check the particular operation to complete in mostly in seconds to minutes. But for a micro operations, in a micro level, the timing is going to be defined in that the particular operation has to be completed. So in 1 clock cycle, there will be equivalent defined micro timing cycles will be defined. In that particular time, the particular operation will be has to be completed. What is the operation to be completed? For example, now is a function R2R. Now this R, I'm using 1 R, I'm redefining it as R0. Other, I'm defining it as R1. For example, if I want to perform operation as R0 is equal to R0 plus R1. So there's one value, data value present at R0, another value present at R1. Now I want to perform operation. What is the operator I'm using here? Addition operation. I'm using the operation addition operation. Now what? In 1 clock cycle, it has to perform first, the ALU has to take the data of R0, and once it comes parallelly, follow-up is next. It has to take R1 value. That also goes into ALU. Now these two values, which are data values, which are taken from R0 and R1, it performs operation in the arithmetic logic unit. What operation? We defined an addition operator, that particular operation, and after performing the result of R0 plus R1, we have to store back in the registers. Which register we have to store back? We are storing back in R0 again. So again, that value will be affected and the resultant value will be stored in the R0 register. All these particular operations has to be completed in one clock cycle. That's what here defining. The micro operation is an elementary operation performed during one clock pulse. On the information stored on one or more registers. Now this is a function we are taken. R is we are taken R is result is f of R comma R. Same I taken 1 R is equal to R naught. Because why taken R naught and R1? Because the data is stored is clearly indicated. It is 1 or more registers. Because of that, I taken 1 R as R naught, another R as R1. When you perform operation and between these two registers, and the operator we have taken here is addition based on this particular operation in one clock cycle. It is going to be completed. Similarly, we have seen a discussion here of performing an addition operation. So similarly, we can use the same registers for subtraction, addition, or logical operation, or XOR, all this. So this is one basic definition of the register language. Next, here in this particular slide, it is defined the internal organization of a computer. Now, internal organization of a computer is defined as it contains a set of registers and their functions. Second one, it contains a micro operation set. What is a micro operation set? Is defining here set of allowable micro operations provided by the organization of the computer. Set of micro operations provided by the organization of the computer. What are set of micro operations here? It can be shift operation, it can be load operation, or it can be arithmetic operation. Arithmetic operation, what are arithmetic? Addition, subtraction, multiplication, or it can be in logical operations like OR, XOR, or NAND, XOR, or AND operation, or you want to clear the data, you want to increment. So there is another is clear, processor control operation is clear, increment means again it is an addition operation, you are adding, decrement, it is an indirect subtraction. So these are the different types of micro operations provided by the organization of the computer. That means each organization supports the different kind of operations. All these different kind of operations we call in a digital system as micro operations. Next one is control signals that initiate the sequence of micro operations to perform. Control signals. Now, what is control signal? Now, this is the key part of the digital system. Now, basically, to understand what is a digital signal, now this digital signal, like to understand, it is a sequence of operations predefined. So, to perform that particular related function, that signal will be enabled by the control operation. See, now in the previous just few seconds before we discussed it, R naught is equal to R naught plus R1. What is the operator we are using here? Addition operator. Now this is a control signal on which we have to perform operation. Now control signal has to define this particular operation. Instead of that, if it is generated in micro operation as minus symbol, then it indicates subtraction. Now the result will be wrong. What is the operation? So it is an addition operation. So this particular control signals that initiate a sequence of micro operations to be performed in the functions, in the where it perform the operation in the arithmetic logic unit. That's what is defined here. Control signals that initiate the sequence of micro operations to perform in the ALU is taken control by the control unit. The same control function in a digital system, we call it as control unit. So that is other part of the register transfer languages in sequence you have to understand. There are different micro operations. So these micro operations in sequence which is going to be controlled, there will be control signals. Where these control signals are present, these control signals are present in the control unit in sequence when and where that signal required. It generates to perform on the data stored in the registered taken into the ALU, arithmetic logic unit, as a function. After performing that particular operation, again it is taken back where the result has to be stored in the resultant registers. Next one is the symbolic notation used to describe the micro transfer among the registers is called register transfer. Symbolic notation. Symbolic notation means here. What is symbolic notation? Nothing but you want to perform addition between two data and addition between two data values. Addition between two data values. One data value, first data value assumed as 0, 8. Second data value assumed as 0, 9. Now these two data values have to store in the registers. I have stored in the register R0 and the register R1. And third one is after the result, final result of R0 plus R1, I have to store in R. Then what happens? Notation R2 indicating R1 is R0 plus R1 plus R1. This is a notation. This sequence of notation is called symbolic notation, what we are defining is called register transfer. The same thing in a symbolic representation for performing micro operations, it is defined. Here, registers transfer are designated with a capital letter, sometimes followed with the numbers. Sometimes followed with the numbers A, R, R13, IR. IR is often the names of indicated function as MAR, memory address register, PC, program counter, IR, instruction register. Information transfer from one register to another register is designated in symbolic form by using a replacement operator. R1, this arrow indicates a transfer of data from R1 to R2. Registers and their content can be viewed and represented in various forms. A register can be viewed as a single entity. Here, one of the indication of this memory transfer is memory address register. Where we use memory address register will come up in the later point. I will explain. Presently, I want to explain more on the registers on the capital indication A, R0. As previously just now I defined that a registers may be present in the micro operations of a digital system are A to 12 different. Now this A to 12, some of the registers I defined, there are 8 basic registers means R0 to R7 are 8 registers. That means R0, R1, R2, R3, so on, R7. These are the 8 registers. In addition to that, we are going to have other registers also for micro operations, and we can define with the names as A and B. A stands for accumulator, A stands for accumulator, and B stands for B type register to support the operations performed along with the accumulator. So overall, I said here A to 12. How many registers now it happened here? 8 registers, and these 2, 1, 2. Totally now it became 10 registers. So depending the design, we take out the number of registers defined for the micro operations to be performed in the digital system. In this way, the first line should be clear that there are registers defined with different symbols. R13 is taken. R13 is taken means in the particular micro operations of digital system, the number of registers are defined more than R7. Then we define a name with R13. Getting it clear? Next is, here it is defined with instruction register. Internal to the micro operations, we have a system register, micro operation register called instruction register. In a later on, we'll discuss what is instruction register, what is memory address register, what is program counter and instruction register. We'll try to understand. Presently, I'm concentrating more on the naming of the registers. That too, these registers has to be named what way it is defined in the capital C. Now, this will give a much clarity here. Registers may also be represented showing the bits in data they contain. Now, as I define a register showing individual bits. Now, 0 is 1 bit, 1, 2, 3, 4, 5, 6, 7, total 8 bits. Just now define now. Now, how many? This is 8 bits. The data always entered into the registers from the left side and leaves from the right side. So, now if I want to store, for example, 0101 and 0110. Now here, this is, as we know that this least significant bit, this is most significant bit. Now the least significant bit enters here 0. Now it is in the 7th position. Next, if say 1 enters, 1 entering here, now the 7th bit will be moved into the 6th bit. So in the position will be 1, 0. Next, if you move 1, next bit position, now it will be 5th bit it goes, it will be 1, 1, 0. In this way, when the most significant last bit enters, the bit positions from 7 on to 0 will be 0, 1, 0, 1, 0, 1, 1, 0. In this way, the data is going to be entered into the registers in a respective bit positions as it indicates from 0 to 7. Here 0 stands for least significant bit position. 7 is the most significant bit of the 8 bits which is defining here. Now the second one, you see the number of registers. You see here is taken one example of 8 bit. Next you see here it's shown example R2 a register which is storing how many bits? 0 to 15 means it is able to store 16 bits. Here, it is able to store 8 bits. That means the bit positions here we are including is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are the bit positions or indicating here for the R2. Here, that means the data size is more than 8 bit. Here, 8 bit is 1 byte. We can store in a register. But this register is having a higher capacity where it can store word length. A word is equivalent to 16 bits. 0 to 15 is 16 bits. So, 16 bits means 2 bytes is equal to 8 plus 8. That means 16. So, the data storage in this register is increased double of a byte. In this way, we define again here also same. Here, 0 means least significant bit of the word and 15 means most significant bit of the word. In this way, it is defined. So, depending upon the digital system, the size of the registers are defined. The bit positions are also indicated in the similar pattern. Next, portion of the registers. Now you can see, just now I explained in this slide. Now this is 8 bit. This is a 16 bit. In 16 bit, what I define? It will be a word length. In this word length, basically, it contains 2 bytes. I said word is equal to 2 bytes. 2 bytes means 2 8-bit portion. This 2 8 bits, now here in the next, it is indicating as a registered portion of the register. If it's a 15 bit, you can see here 0 to 7 is taken 1 byte. Next is 8 to 15. is taken as another byte. 0 means 0, 1, 2, 3, 4, 5, 6, 7. In this way, 8 bits. Now it is taken as 8-bit data. Next, you can see here, same way. Same way, if you take 8 to 15, 8, 9, 10, 11, 12, 13, 14, 15. So these are another 8 bits. If you see 0 to 7, this is the least significant bit of the byte. This is the most significant bit of the byte. Next, you can see this is the least significant byte of the another byte, and this is the most significant byte of the another byte. Now, we have to understand 16 bits. We can say L. What is L stands for? What is H? L stands for lower byte of the 16-bit word. H is the higher byte of the 16-bit. In this way, lower byte, it can store 8-bit value. Higher byte, it can store 8-bit value. The combined data represents a 16-bit. That's what is indicating. Now, here the subfields indicates these are. What is PC stands for? PC stands for program. PC stands for program. PC stands for program counter. Always a program counter is a 16-bit register. A 16-bit register, we are defining it as a program counter. The operations of program counter in the coming class we are going to discuss. Since it is 16-bit register, we have in the register transfer language how the storage is done for 16-bit is been indicated. In this way, the data storage are going to be. Now, the portions of 8-bit and 16-bit are defined like this. What are the functions? Control function. Control function means nothing but, you should not get confused. A control function here defined here as control signal. The signals are defined from the control function. Here, now it is being defining the control function. The actions are performed. The actions performed only when certain conditions are true. This is similar to an if statement in a program. In digital systems, this is often done by a control signal called a control function. A control function is a Boolean variable. If the signal is 1, the action takes place. That means here, one point I should make it clear to you. Boolean variable means the user at the front-end system is defining is a high-level language. And here, this high-level language, now what subject of micro operations we are studying, it is basically can understand is low-level language. This is middle-level language. User, whatever defining at the front-end system is a high-level language. So this has to be converted into the middle-level language. Again, this has to be converted into the low-level language. This low-level language also we call it as machine level language, or it also we call it as Boolean variables. Boolean variables means the binary, that particularly follows binary number system. The value of binary means it may be 0 or 1. That means the basic discussion of the register transfer language, the control function which performs on this register transfer language is on zeros and ones. We define here the numerical values in the high level language, which is going to be converted into the machine level language. This machine level language is called as micro operations performed. So whatever the conditions you are applying here, if there are statements here, you see if statement in the programming language, same applies at the control function at the Boolean variable at the machine level language. That's what we are defining. Now, if the signal is 1, the action takes place. This is represented as P. P means processing data. What is the process operation? R2, R1 to R-less. You can say right to left. That means R1, it's having a value 0.8 and R2 is having a value 0.9. For example, this symbol represents is moving a value of R1 to R2. How? Once this operation is over, P indicates that R2 value is now 0.8 and R1 value remains 0.8. That means you have moved a value from R1 to R2, replacing the present value present in the R2 with a new value which is coming from the R1. This operation process, representation process, we call it as define. That means reflecting operation we are performing from right to left. That usually going to be same continuation here, R1 comma R2. This is clear. If P is equal to 1, you can see here, if the signal is 1, then action takes place. Then it is showing, if signal is 1, if P is equal to 1, load the contents of the register R1 into register R2. P is equal to 1, then R1 value, that's previous just now shown, R1 is equal to 0.8, R2 is equal to 0.9. Now P is equal to 1. P is equal to 1. What happens? The value of R1, we have to move into R2. The representation right to left, R1 is pointing to R2. Implement. So implementation of control operations. See, this is control circuit. P is equal to 1. P is equal to 1. Clock is enabled in one clock cycle. Now the value N is what? N is equal to 8 bits. N is equal to 8 bits. Let's take an example. Now this value has to be moved to R2. Now what is the new value now in R2? R2 will be 0.8 replacing 0.9. That is the indication of this particular operation from previous slide we are defining. Now coming back. Till now you see in one clock cycle the operation has to be performed. One clock cycle. Now what happens here, you can see the same clock controls the circuits to generate the control function and the destination register. One clock is equal to, you can say here, it is indicating that one, here it's a pulse. Clock is this particular, we are representing in a pulse. Now you can see this is a representation is showing here. Now what happening here, the basic operation starting at this point. The basic operation starting at this point. At T, it loads. At T plus 1, the transfer, it is going to be happen. And next T plus 2, the data is going to be stored. So finally, this one clock pulse, now at the initial state, it's starting an operation. Next at T plus 1, it loads the value. And T plus 2, it moves to the next step. It moves to the R2, replacing the value of R2 with R1. So in the next plus what? T plus 3 cycle, next cycle. Now it replaces here. Now in the final T plus 4 state, it checks that the R1 value is equal to 0.8 and R2 value is equal to 0.8, replacing 0.9. Replacing 0.9. So this is one clock cycle, how it is implemented. It's shown in this particular slide. Now here in this you can see there are two or more operations are to occur simultaneously. They are separated with columns. You can see here one operation is process instant R5 to R3. The data from R5 you have to move into R3. Next is instruction register is pointing. Here you can see to the MAR means memory address register. The value of present in the instruction register, you have to move into the memory address register. So these are the two operations performing. This is the first operation. This is the second operation. So two operations performing separately. Then you have to indicate a micro operation by defining them. You can see using a comma. Using a comma, you have to differentiate. That means in one clock cycle, there are two different operations are performed in the same clock cycle. Then these two operations are two different operations. You have to indicate with a comma as we shown here. That is a differentiation that it's differentiating, separating with a comma. This is different operation. This is different operation. How we have to indicate this in the register transfer language? This is a notation we have to indicate. Next one is Here, if the control function P is equal to 1, the contents R5 into R3 is moved. At the same time, the load, the contents of registers IR into the register MAR, memory address register, is done. The basic symbols used for register transfer language is letters and numerals to denote a register. So, example MAR, IR, R2. Now, if it is a parenthesis, brackets are used to denote a part of the register. Example R2 parenthesis brackets 0 to 7, comma R2 parenthesis bracket L. Arrow to denote we are using to transfer of information. Example R2 to R1. Next is comma. It separates two operations like we seen R1 to R2 with an arrow indicating operation, comma R4 to R3. Getting it clear? In the next session, next topic will take in. Today we discussed about register transfer language. We discussed in detail about the register transfer notations and operations in a digital system. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.